Welcome to this video session. The topic that we are going to cover in this session is properties of acids and bases. Children, you are already aware of the fact the sour and bitter tastes of food are due to acids and bases respectively present in them. Let us now begin with our topic, starting with a few daily life examples of acid and bases. If someone in the family is suffering from a problem of acidity after overeating, which of the following would you suggest as a remedy? Lemon juice, vinegar, or baking soda solution? Which property did you think of while choosing the remedy? Surely you must have used your knowledge about the ability of acids and bases to nullify each other's effect, right? And so, when someone is suffering from acidity, the remedy that you can give is baking soda solution, as this will neutralize the excess acid and result in immediate relief. Let us now talk about what are indicators. Indicators, as the name suggests, indicates about the nature of the substance. That is, whether it is acidic or basic in nature. Let us talk about the first natural indicator, which is litmus. Litmus solution is a purple dye which is extracted from lichen, a plant belonging to the division Thallophyta, and is commonly used as an indicator. When the litmus solution is neither acidic nor basic, its color is purple. It is now available in two forms, which are red and blue litmus. Acids which are sour in taste turn blue litmus to red color, and there is no change in color in case of red litmus. Similarly, bases which are bitter in taste change red litmus to blue color, and there is no change in the color of blue litmus paper. Turmeric is another such indicator. Have you noticed that a stain of curry on a white cloth becomes reddish brown when soap, which is basic in nature, is scrubbed on it? It turns yellow again when the cloth is washed with plenty of water. Why? Because then the basic soap gets removed with water. So, students, turmeric is a natural indicator. It contains natural yellow dye. It turns red in basic solutions. The red cabbage obtained from red cabbage leaves is also a natural indicator, and that is red in color. It remains red in acidic solutions and turns green on adding basic solutions. The colored petals of some flowers like hydrangea, petunia, and geranium also change color in the presence of acids and bases and act as an indicator. For example, the flowers of hydrangea plant are blue in color and they turn pink in the presence of basic solutions. You can also use synthetic indicators. Synthetic indicator means the indicators which are derived chemically, such as methyl orange and phenolphthalein, to test for acids and bases. The color of methyl orange indicator in natural solution is orange. It gives red color in acidic solution and gives a yellow color in basic solution. The color of phenolphthalein in natural solution is colorless. It remains colorless in acidic solution and gives a pink color in a basic solution. Let us conduct an activity and see how different substances change color with different indicators. Collect the following solutions from the science laboratory: hydrochloric acid HCl, sulfuric acid H2SO4, nitric acid HNO3, acetic acid CH3COOH, sodium hydroxide NaOH, calcium hydroxide CaOH2, potassium hydroxide KOH, magnesium hydroxide MgOH2 and ammonium hydroxide NH4OH. Put a drop of each of the above solutions on a watch glass one by one and test with a drop of the indicators shown in the table. What change in color did you observe with red litmus, blue litmus, phenolphthalein and methyl orange solutions for each of the solutions taken? Tabulate your observations in a table. These indicators tell us whether a substance is acidic or basic by change in color as shown in the table. There is one more type of indicator, which is olfactory indicator. The term olfactory means relating to the sense of smell. Those substances whose smell changes in acidic and basic medium are called as olfactory indicators. For example, onion and vanilla extract. Onion has a characteristic smell. If a basic solution like sodium hydroxide is to be added to the onion smell cannot be detected. However, an acidic solution does not destroy the smell of onion. Vanilla extract has a characteristic pleasant smell. If a basic solution like sodium hydroxide is added to vanilla extract, we cannot detect the smell of vanilla extract. However, acid cannot destroy the smell of vanilla extract. Friends, in this video, we studied the properties of acids and bases. In the next video, we will learn about reactions of acids and bases. Hello friends, welcome to this video session. The topic that we are going to cover in this session is reactions of acids and bases. In this video lesson, we will understand the behavior of acids and bases in a better way and understand how acids and bases react with metals, metal carbonates, metal hydrogen carbonates, metallic oxides and non-metallic oxides. We will also learn how do acids and bases react with each other and what is the special name given to such a reaction. Let us now begin with the first reaction, that is, reaction of acids with metal. Let's see how a metal reacts with acids with the help of an activity. Set the apparatus as shown in the figure. Take about 5 ml of dilute sulfuric acid in a test tube and add a few pieces of zinc granules to it. What do you observe on the surface of zinc granules? You will observe the formation of gas bubbles on the surface of zinc granules. Pass the gas being evolved through the soap solution taken in a trough by means of a glass tube. Why are bubbles formed in the soap solution? Take a burning candle near a gas-filled bubble. What do you observe? The gas present in the soap bubble burns with a pop sound, making a little explosion. And students, only hydrogen gas burns with a popping sound. This shows that hydrogen gas is evolved in the reaction of zinc granules and sulfuric acid. Repeat this activity with some more acids like hydrochloric acid, HCl, nitric acid, HNO3 and acetic acid, CH3COOH. Are the observations in all the cases the same or different? And you will observe a similar observation in all the cases. Therefore, we can conclude that metal reacts with acids to form salt and hydrogen gas. Let's now talk about the reaction of bases with metals. When a base reacts with a metal, then a metal salt and hydrogen gas are formed. For example, when sodium hydroxide solution is heated with zinc, then sodium zincate and hydrogen gas are formed. We can show the formation of hydrogen gas in the reaction of sodium hydroxide solution with zinc metal by using the same experimental setup as we have used to study the reaction of metal with acids. So, we can conclude that both acids and bases react with metals to form salt and hydrogen gas. Let us now move ahead and discuss the reaction of acids and bases with metal carbonates and metal hydrogen carbonates. First, we will discuss about acids. So, acids react with metal carbonates and metal hydrogen carbonates to form salt, carbon dioxide, and water. Let us understand this by an activity. Take two test tubes. Label them as A and B. Take about 0.5 grams of sodium carbonate, Na2CO3, in test tube A and about 0.5 grams of sodium hydrogen carbonate, NaHCO3, in test tube B. Add about 2 ml of dilute HCl to both the test tubes. What do you observe? You will observe that brisk effervescence of a gas is produced. Pass the gas produced in each case through lime water, calcium hydroxide solution as shown in figure, and record your observations. You will observe that the lime water turns milky, which shows that the gas evolved is carbon dioxide. Keep on passing the carbon dioxide through the milky lime water for some time. The lime water becomes clear again. This shows that the white precipitate of calcium carbonate dissolves on passing excess of carbon dioxide gas. We can repeat this experiment by replacing metal carbonate with metal hydrogen carbonate, that is, sodium hydrogen carbonate. Again, we will get carbon dioxide gas, which will turn lime water milky. On passing excess carbon dioxide, the milky lime water will become clear once again. Now, if we talk about bases, bases do not react with metal carbonates and metal hydrogen carbonates. You must be wondering why? Because both metal carbonates and metal hydrogen carbonates are basic in nature. Let us now move ahead to the next type of reaction, that is, the reaction of acids with bases. When an acid reacts with a base, then a salt and water are formed. Let us know about it through an activity. Take about 2 ml of dilute NaOH solution in a test tube and add 2 drops of phenolphthalein solution. What is the color of the solution? The solution will turn pink. Add dilute HCl solution to the above solution drop by drop. Is there any color change for the reaction mixture? We will observe that after adding some amount of HCl, the pink color disappears and the solution becomes colorless. Why did the color of phenolphthalein change after the addition of an acid? This is because at this stage, the entire sodium hydroxide base taken in the test tube has been neutralized by hydrochloric acid. The color of phenolphthalein changes from pink to colorless because no more sodium hydroxide base is left unreacted in the test tube. Now, add a few drops of NaOH to the above mixture. Does the pink color of phenolphthalein reappear? Why do you think this has happened? This has happened because after adding a few drops of sodium hydroxide solution, the reaction mixture has become basic again. Now, let us take one more example. If hydrochloric acid is treated with a base like sodium hydroxide, then neutralization occurs and there is a formation of sodium chloride, salt and water. The base neutralizes the acid and destroys its acidity. Since an acid and a base neutralize each other's effect, so the reaction between an acid and a base to form salt and water is called neutralization reaction. Now we will discuss the next type of the reaction, which is reaction of metallic oxides with acids to form salt and water. And students, you already know that metal oxides are basic in nature, and therefore what we can say about the reaction of bases with metal oxides? Yes, right. Bases do not react with metal oxides. So, let's discuss an example of reaction of acids with metal oxides. Say copper. Second oxide is a metal oxide. To it, add dilute hydrochloric acid. It reacts to form copper second chloride and water. Let's conduct an activity to understand this reaction in a better way. Take a small amount of copper oxide in a beaker and add dilute hydrochloric acid slowly while stirring. Note the color of the solution. What has happened to the copper oxide? You will notice that the color of the solution becomes blue-green and the copper oxide dissolves. The blue-green color of the solution is due to the formation of copper second chloride in the reaction. So, we can conclude that acids react with metal oxides to form salt and water. But wait, do you observe any similarity between this reaction and neutralization reaction? Yes, children, this reaction is a kind of neutralization reaction. Why? Because metal oxides are actually basic in nature and therefore This reaction becomes a reaction of acids with bases. Let's now discuss the reaction of bases with non-metal oxides. These non-metal oxides are acidic in nature and therefore resemble the neutralization reaction. Bases react with non-metal oxides to form salt and water. If we try to take a broader look, we can observe that non-metal oxides are acidic, right? So, this reaction is basically the reaction of base with acids. The bases react with non-metallic oxides to form salt and water. For example, calcium hydroxide, which is an alkali, carbon dioxide, which is a non-metallic oxide, reacts with it to form salts and water. Friends, in this video, we have studied the reactions of acids and bases. In the next video, we will learn about the commonalities of acids and bases. Hello friends, welcome to this video session. The topic that we are going to cover in this session is commonalities of acids and bases. Students, as you know, that all acids have same properties, and similarly, all bases have same properties. So what is the reason behind this? There must be something common in all acids causing acids to have same properties. Also, there must be something common in all bases which cause them to have same properties. In this session, we will decode this something which is common in all acids and all bases. Let us now first discuss about acids. That is, what do all acids have in common? For this, we will first conduct an activity. Take solutions of glucose, alcohol, hydrochloric acid, sulfuric acid, etc. Fix 2 nails on a cork and place the cork in a 100 ml beaker. Connect the nails to the 2 terminals of a 6-volt battery through a bulb and a switch, as shown in the figure. Now, pour some dilute hydrochloric acid in the beaker and switch on the current. What do you observe? The bulb starts glowing. This shows that hydrochloric acid solution taken in a beaker conducts electricity. If we repeat this experiment by taking sulfuric acid, the bulb glows again. This shows that sulfuric acid conducts electricity. In fact, all the acid solutions conduct electricity. Glowing of the bulb indicates that there is a flow of electric current through the solution. The electric current is carried through the acidic solution by ions. Now, repeat the experiment separately with glucose and alcohol solutions. What do you observe now? Does the bulb glow in all cases? The bulb does not glow in both these cases. This shows that glucose and alcohol solution do not conduct electricity. The aqueous solution of an acid conducts electricity due to the presence of charged particles called ions in it. So, all acids contain hydrogen ions. The hydrogen ions present in acids is such that when acid is dissolved in water, it separates out as positively charged hydrogen ions and enters the solution as H+ ions. So, we can say that an acid is a substance which dissociates on dissolving in water to produce hydrogen ions or H+ ions. So, the common thing in all the acids is that they produce hydrogen ions when dissolved in water. Let's now move ahead and discuss about what do bases have in common. First of all, we need to understand that not all the bases dissolve in water, but some bases dissolve in water and they are called as alkalis. Now, whenever we will talk about base in this discussion, we will be talking about these water-soluble bases known as alkalis. Now, we will conduct a similar experiment as we have done for testing about acids by taking bases like sodium hydroxide or calcium hydroxide. And the bulb starts glowing. This shows that basic solution taken in a beaker conducts electricity. Glowing of the bulb indicates that there is a flow of electric current through the solution. The electric current is carried through the basic solution by ions. So, we can conclude that when a base is dissolved in water, it always produces hydroxide ions, OH-. For example, sodium hydroxide is a base because it dissolves in water to produce hydroxide ions. So, we can conclude that a common property of all the bases or alkalis is that they produce hydroxide ions when dissolved in water. In this video, we studied the commonalities of acids and bases. In the next video, we will learn about pH. Hello friends, welcome to this video session. The topic that we are going to cover in this session is pH scale. So students, you already know that some acids are strong while some acids are weak in strength. Similar is the case with bases. We have strong and weak bases. How do we measure the strength of acids and bases? We use the pH scale to determine the strength of acids and bases. Students, the first thing that you need to be aware about is that acidic solutions have excess of hydrogen ions. Also, you should note that even the acidic solutions contain hydroxide ions, which comes from the ionization of water, but its concentration is too less. Similarly, basic solutions have excess of hydroxide ions, but they also contain hydrogen ions, but the concentration is too less. So, both acidic solutions as well as basic solutions contain hydrogen ions. In 1909, Sorensen devised a scale on which the strength of acid solutions as well as basic solutions could be represented by making use of hydrogen ion concentration. This scale is known as pH scale, that is, potens, originally German word of power, or in simple words we can say power of hydrogen ions. Sorensen linked the hydrogen ion concentrations of acid and base solutions to the simple numbers from 0 to 14 on his pH scale. In simple language, pH should be seen as a number that represents the acidity or basicity of which solution. The higher the concentration of hydrogen ion, the lower its pH. It is important to note that pH is only a number and has no units. You should also know that neutral substances, such substances which are neither acidic nor basic, have a pH of exact 7. For example, pure water is a neutral substance and therefore it has a pH value 7. So, the substances with pH is equal to 7, that is, the neutral substances, will have no effect on indicators like methyl orange or phenolphthalein. Now, let's talk about the pH of acidic solutions. Acidic solutions have a pH of less than 7. For example, say a solution having a pH of 4 will be acidic in nature. It is also important to note that more acidic a solution is, the lower will be its pH. For example, a solution of pH 1 is much more acidic than another acid having pH of 6. So, all the solutions have pH less than 7 are acidic in nature, and hence they turn blue litmus red, and also they turn methyl orange indicator red. Now, we will further this discussion by talking about pH value of bases. Basic solutions have a pH of more than 7. For example, a solution of pH 11 will be basic in nature. Also note that the more basic a solution is, the higher will be its pH. For example, a solution of pH 14 will be much more basic than another solution of pH 10. In simple words, a solution of pH 14 will be much stronger base than another solution of pH 10. So, the higher the pH, the stronger the base. All the substances having pH more than 7 are basic in nature, and hence they turn red litmus to blue, and they turn phenolphthalein indicator pink. So students, we can conclude that at pH 7, a solution is neutral. As the pH of a solution decreases from 7 to 0, the hydrogen ion concentration in the solution goes on increasing, and hence the strength of acid goes on increasing. On the other hand, as the pH of solution increases from 7 to 14, the hydrogen ion concentration in the solution goes on decreasing, due to which the strength of base also goes on increasing. In this video, we studied the pH scale. In the next video, we will study about salts. To this video session, the topic that we are going to cover in this session is salts. First of all, we will try to understand that what are salts. A salt is a compound formed from an acid by the replacement of the hydrogen in the acid by a metal. We will understand more about salts in detail. Let us understand with the help of an example. Hydrochloric acid is HCl. Now, if we replace the hydrogen of this acid by a metal atom, say sodium atom, then we will get a salt, NaCl. This is called sodium chloride. It is a salt. This is the best known salt, and it is the same salt that we use in the kitchen, known as common salt. Salts are formed when acids react with bases. In a way, we can say that a salt has two parents, an acid and a base. So, the name of a salt consists of two parts. The first part of the name of salt is derived from the name of the base. And the second part of the name of the salt comes from the name of the acid. For example, the name of a salt, sodium chloride, sodium comes from sodium hydroxide, which is a base, and chloride comes from hydrochloric acid, which is acid. Students, let us now discuss about the properties of salts. Salts are mostly solids. They have a high melting and boiling point. They are usually soluble in water. Just like acids and bases, the solutions of salts in water conduct electricity. Salt solutions conduct electricity due to the presence of ions in them. Salts are ionic compounds. Every salt consists of a positively charged cation and a negatively charged anion. For example, a salt NaCl has Na plus cation and Cl minus anion. Now, let us discuss about the different families of salts. The salts having the same positive ion or the same negative ion are said to belong to a family. For example, sodium chloride and sodium sulfate both belong to the same family of salts called sodium salts. Why? Because they both contain same positively charged ions, sodium ions, Na+. Similarly, sodium chloride and potassium chloride belong to the same family because they have same negatively charged ion, that is Cl- ions. Some of the important families of salt are sodium salts, calcium salts, magnesium salts, zinc salts, carbonate salts, and acetate salts. Now, we will discuss about most important topic, which is the pH of the salt solutions. As you know, that a salt is formed by the reaction of an acid and a base. We might expect the salt to be neutral in nature. Though the aqueous solutions of many salts are neutral, but some salts produce acidic or basic solutions when dissolved in water. The acidic nature and the basic nature of some salt solutions can be explained on the basis of hydrolysis of salts. Firstly, the salts of strong acids and strong bases give neutral with pH is equal to 7. For example, sodium chloride is formed from a strong acid, hydrochloric acid, and a strong base, sodium hydroxide. So they produce a neutral salt. Secondly, the salts of strong acids and weak bases give acidic solution, pH less than 7. Let us understand this with the help of an example. Ammonium chloride. It is formed by a strong acid, hydrochloric acid, and a weak base, ammonium hydroxide. And so, the salt obtained is acidic in nature. Finally, the salts of weak acids and strong bases give basic solutions or alkaline solutions. For example, sodium carbonate salt is formed from a weak acid, carbonic acid, and a strong base, sodium hydroxide. And so, the salt obtained is basic in nature. And friends, do you know? That is, ordinary salt, sodium chloride, is an important raw material for the substances of our daily use. For example, 1. For the production of sodium hydroxide and chlorine. The various uses of the three products resulting from this process are shown here. This process is called the chlor-alkali process. 2. In the production of bleaching powder. The electrolytic decomposition of sodium chloride produces chlorine gas, which is used in the production of bleaching powder. Bleaching powder is used in the textile industry, paper factory, chemical industry, and drinking water to get rid of bacteria. 3. In the production of baking soda, baking powder, and washing soda. So friends, in this video, we studied about salts.